it wasn't just the right process, right?
It would be right answer. One digit off, but I mean, the right is 1.77.
Yeah, I got
1.7778, I don't mind.
I mean, he was there.
Okay, so learn from the mistakes. Hopefully the worst is over, right? Okay, good. So yes, the final is comprehensive. So you will have.
Can you ask that one with the CSS question so I can try to?
There will be one multiple choice like that. Yes, there will be one.
The final exam would just be a series of all the
All the multiple choice. All the
like
ones
100
we all
multiple
got
choice.
wrong.
100 multiple choice. Yeah.
Let's see. I haven't, started on the final. I haven't even thought about the final exam yet.
Well, we can take it off your hands and write it for you.
All right, guys, let's start the chapter. Electrochemical reactions. So, electrochemistry, as the word suggests, studies relationship between electricity and chemical reactions. Now, electrochemical reactions, one more thing to remember, electrons are being transferred from one species to another. Of course, we know that electricity is flow of electrons, right? So, electron flow in chemical reactions, that's what is electrochemistry is all about. Now, this is little bit revision in the beginning of this chapter. We had in chapter 4, we learned about redox reactions, reduction, oxidation. So, oxidation reduction reactions, we call it redox reactions. And redox reactions involve electron transfer from one species to another, right? Now, couple of things to remember or recalling. Oxidation numbers. Remember what is oxidation, what is reduction? Okay, or in other words, what did we use, guys? We used oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. I'm old, guys. That is how I keep track of them.
I like that.
Okay? Oil rig. Well, maybe you remember this.
No, I just remember what oxidation reduction is.
Leo the lion says, grrr. Loss of electrons is oxidation. Gain of electrons is reduction. Okay? Something, doesn't matter. As long as you remember oxidation is electron losing, and when you gain electrons, it is reduction. I'm good. Yes?
Now, I can never remember, when you're doing charges, the sign is supposed to go on one side. When you're doing oxidation numbers, the sign is supposed to go on the other side.
Yes.
Which is it? Is it the way they had it written?
When you write the charges, we usually write, see, for example, right here, look at here, for that sink. Sink 2 plus, that 2 plus which is written on the top is the charge, ions charge. So you write the number first and the charge symbol second, 2 plus. But when you write the oxidation number, the bottom one, that number is plus 2, that is its oxidation number. So you write the sign first and then the number.
I always put those or don't remember which order they're supposed to go in.
Okay. So, well, people usually, kind of write that, and I usually don't punish you for writing that way. But when it comes to oxidation reduction, it's a good practice to keep track of them the way you write it. Otherwise, you yourself will get confused, because not always charges are the same as oxidation states. Okay? So, now, in a redox reaction, we already just said that oxidation reduction means electrons are transferred from one species to another. That means somebody is losing electron and someone else is gaining electrons. So to keep track of who is getting what or who is losing what, we assign oxidation numbers. So this reaction, zinc, solid zinc and 2 hydrogen ions gaining, forming zinc 2 plus and H2. This reaction, the oxidation numbers are assigned. Do you remember how do we assign oxidation states? I know this is done so early in the previous semester and you guys might have done it a long time ago. So I think I have a couple of slides which will remind us the rules for assigning oxidation numbers. Let's look at that. Oh, where is that? Okay, right here. Come down. Okay, before the rules, come some more, recalling from all the old stuff. So the species which is oxidized, as we said, when it loses electron, because oxidation is loss of electrons, right? So when somebody is losing electron, we will say that species is oxidized. So for this example, zinc, which had 0 oxidation number, it became zinc 2 plus ion. How does zinc becomes zinc 2 plus? When it loses 2 electrons, right? When 2 electrons are removed from the neutral zinc atom, it becomes a zinc 2 plus ion. So we will say zinc is oxidized because it lost 2 electrons to go from the neutral zinc to zinc 2 plus ion. Similarly, a species is reduced when it gains electron. Let's look at hydrogen. Here H plus, right? And on the right side we see that as H2. If you recall, pure stuff has oxidation state of 0. So H2 pure state, it is 0. Why? H plus, each H plus has gained an electron, therefore it is 0 now. So we will say hydrogen is reduced. Now the confusing part, the name. What is reduced is called the oxidizing agent. So hydrogen is called the oxidizing agent. Hydrogen gets reduced, but we call it the oxidizing agent. So the species who does the oxidation, the species who gets reduced is the oxidizing agent. The other way is also right. The species that gets oxidized is the reducing agent. That is how we call it. So I don't know the problem. I think somebody was really confused when they came up with all these names and we are supposed to follow that now. So similarly, what is oxidized is the reducing agent. So zinc was oxidized, so we call zinc the reducing agent. Okay, now we are going to look into those section 4.4, the just revision of the assigning oxidation numbers. If you want, you can open your book to section 4.4 because here I have only just bullet points. Probably you might have little more detail in there. 4.4 is which page, guys? 4.5. Okay, page number 137, that is where you have the rules. Page number 137, you see oxidation numbers, and we are going to, like you can see that following rules for assigning oxidation numbers. So there are those 4 rules, that is what we are going to look at. So the first thing is elements in their pure state, elemental form, has an oxidation number of 0. The second rule is the oxidation number of a monoatomic ion is the same as its charge. So in the book, if you look in that section, you have a little more stuff in there. It's a good practice. Let's just revise ourselves on these rules. So any monoatomic ion, the oxidation number equals the charge on the ion. So say for example, K plus has an oxidation, I'm reading from the book. So K plus has an oxidation number of +1. S2 minus has an oxidation number of -2, so on. Now it further says the alkali metal ions or group 1 metal ions always have an oxidation state of +1. They also form +1 charge or 1 plus ions all the time, right? Now group 2, they always have +2 and aluminum is +3. And here it says, in writing the oxidation numbers, we will write the sign before the number to distinguish them from the actual electronic charges or electric charges. The charges we will do number first and then the sign. Okay, so that is the notation. Now rule number 3, which is for non-metals. Non-metals usually has negative oxidation numbers, although some of them are positive in some cases. Now for oxygen, most of the time oxygen is -2, just like most of the time oxygen is 2- when it is an ion, right? So most of the time it is -2, but in peroxide, which is O2 2-, oxygen's oxidation number is -1. Then comes hydrogen. Hydrogen is when it is bonded to non-metals, hydrogen will act like the positive ion, or it will be +1. But when it is bonded to metals, it will be -1. So hydrogen will have an oxidation number of +1 or -1 based on how it is bonded in the compound. To non-metals, remember the positive charge or the balancing come from hydrogen, so hydrogen is going to be positive, whereas metals, hydrogen is negative because metals will be always positive. Then furthermore, if you keep reading for non-metals, fluorine. Fluorine has an oxidation number of -1 always. Rest of the halogens, most of the time -1, but they can be positive when they are bonded to oxygen, like chlorate and perchlorate, chloride, all that ions where chlorine is bonded to the oxygen, oxyanions. In those cases, chlorine will become positive, oxygen will be negative. So except oxygen, in other cases, halogens are negative. Now when halogens bond themselves, like you have compounds like IF7, iodine heptafluoride, fluorine will be -1, but that time iodine will be +7 in that compound. So halogens, as I said, mainly -1, that's what you have to remember. But if they are bonding with themselves, one of them could be positive. If they are bonded to oxygen, they will be positive. Now the sum of the oxidation numbers in a neutral compound will be always 0. So all the positive charges and all the negative charges should add up in a neutral compound. Just like that, the negative oxidation numbers and positive oxidation numbers should cancel each other and you should get 0. And what about a charged species, a polyatomic ion? The sum of the oxidation numbers should be the same as the charge on the species, like SO4 2-, sulfate ion. When you calculate the oxidation numbers of oxygen and sulfur, and when you take the sum of all that, you should get 2-. So these are the rules to remember when you assign oxidation numbers. Do you need practice on this? So remember how we did that whenever we need to do oxidation numbers, whichever oxidation number you don't know, which species you are looking for, assign that as an X and then put the oxidation numbers of the other things and write like an algebraic equation, X plus whatever you have is equal to, if it's a neutral compound it's 0, if it's a polyatomic ion, the charge, and then solve for X. That is how you get the oxidation numbers. Okay, so, I guess we have a practice exercise. So let's just look at that. Maybe that will remind us and bring us back to track with oxidation numbers. Where is it? 20.1. 20.1 is in
Page 845.
845? Okay. 839, 849. Okay, so the sample exercise, let us look at that first, as we do usually, identifying oxidizing and reducing agents. So here is an equation given to us, cadmium and nickel oxide giving plus water giving you cadmium hydroxide and nickel hydroxide. So we want to find out the substances that are oxidized and reduced. Okay, so when we look at like that, we may not be able to, just by looking at the reaction, we may not be able to say which one is oxidizing, which one is reducing. So what can we do? We can go ahead and assign the oxidation numbers, and then looking at the numbers and remembering oil rig, we can assign which species is oxidized, which species is reduced. So what are the rules we are remembering? So whatever pure species we have, elemental form, they are going to be 0. So cadmium looks like it's in the pure elemental form, right? So that is going to be 0. And then let's look at the nickel oxide. We know that oxygen is -2. So 2 oxygen. So what is the total positive charge there? -4. So nickel has to be +4. Now for water, we know that oxygen is -2, hydrogen +1, yes, when it is non-metal, so oxygen is non-metal, so +1, that is true, so 2 of them, so 2 plus. So for each hydrogen we will call it +1. Now cadmium hydroxide. So hydroxide, so once again oxygen is -2, 2 oxygens, so we have -4 from oxygen, 2 hydrogens +2, so -4 + 2, what is left? To balance, you need another 2 negative charge, right? Or in other words, cadmium has to be +2. Then similarly for nickel, oxygen is -2, 2 of them, so -4. Hydrogen is +1, 2 of them, so +2. So you need another +2, which should be from nickel. Now you can compare before and after. Look at cadmium. Before it was 0, now it is +2. So what happened to cadmium? It lost electrons or gained electrons? It lost electrons. So, or in other words, when the oxidation number goes up, when the oxidation number increase, that means it is losing electrons. If the oxidation number is coming down or reducing, that means it is gaining electrons. Okay, that is one way of looking at it. Or you can think through also logically. It was 0, now it is 2 plus. How do I get positive charges? That many less number of electrons. Or in other words, electrons are lost. So cadmium is losing electrons, therefore it is oxidation is loss of electrons. So the oxidation reaction, or it is oxidizing, right? Now how about nickel? What happened to nickel? It was +4, now it was become +2. What happened? It is reduced, or it was +4 means it had 4 less electrons. Now it is +2. So how the positive charge will come down? It has gained electron, right? So it gained 2 electrons. That is why from +4 it is +2 now. Okay, let's do the practice exercise now. So we have a reaction right there. Let me copy that. The reaction is 2 water and aluminum plus aluminum pure form. What else? Oh, MnO4 minus. I'm just using the species, guys, avoiding the physical states. Yeah, for here you don't care. That is why I'm also OH4. Is there a minus charge there?
Yeah.
Yes. And MnO2, right? Okay. So aluminum here, pure element. What will be the oxidation state? 0. All right, let's do everything. So oxygen here is -2. So hydrogen has to be, how do you write it? +2. You are assigning oxidation state for one single atom, okay? Remember that. You are not looking at the total charges. Okay, you are assigning oxidation state for each atom. So each hydrogen is +1. You have 2 of them. Therefore, you have +2 for to get sum. Okay. All right. Now, how about here? 4 oxygens. Well, oxygen is going to be -2 here. How do we find out manganese charge? That's what we are doing. So 4 oxygen is going to be -8. We don't know what is manganese. So as I said, you can just put manganese as X, and the sum of this should give you what? -1, the charge of the species. Now solve for X. So X is -1 plus 8, which is +7. So manganese has to be +7. That is the oxidation number of manganese. Is that, everyone remember that, right? So this comes from that rule. A charged species, the sum of the oxidation state should be equal to the charge of the ion. Okay, now let's go to this side. Once again we have oxygen here, which is -2. Remember we have 4 of them there, so -8. Hydrogen is +1. We have 4 of them, so +4. We don't know aluminum, so we will just put as +X is equal to -1. Solve for X. What do you get? +3. -8 plus 4, -4. -4 plus X is -1. So bring it to the other side. So +4. So you get +3. Okay, here oxygen is -2. 2 of them. So -4. There is only one manganese. Sum should be 0. So that means manganese has to be +4. So we assign the oxidation state of each. That's all the question is asking, but let us go one step further and let us identify what is getting oxidized, what is getting reduced.
Actually, it wants you to identify the oxidizing and reducing agents.
Oh, it's asking you to identify? Oh, okay, all right.
Before it doesn't, this one does.
Okay, all right, let's identify then. So, hydrogen and oxygen, is there anything happening? Both sides, same numbers? So, of course, they are not the oxidizing or reducing agents, right? So, it has to be manganese and aluminum. Let's check what is going on with each. Aluminum was 0, now aluminum is +3. What happened to aluminum? It lost electrons or got oxidized. Okay, manganese was +7, now it is only +4. That means it gained electrons, so it is reduced. All right, good. Everyone is good so far, right? So now we are going to do, how do we balance oxidation reduction reactions? So whenever we balance redox reactions, there is an additional step. That is, when we usually balance the reactions, we would just obey the law of conservation of mass, right? We will look into the number of elements on each side, and we make sure that the number of each element, number of total number is the same. That is how we balance the equations. But in oxidation reduction reactions, we have to do an additional step, which is the gains and losses of electrons also must be balanced. So the easiest way to do this is called half reaction method. That is all we are going to do today. Learn half reaction method. You love this one? It is fun. When you start doing it, it is fun. You need a lot of focus, but it is fun. So what do we mean by half reaction method? This involves treating, on paper only, the oxidation and reduction are two separate processes. Of course, you know that in the real world, in the chemical reaction, there is no separate process, right? They occur at the same time, oxidation and reduction. But for the ease of keeping track of these things, we are going to treat in paper, these are, the oxidation as a separate reaction and reduction as a separate reaction. And then we will balance each of them. And at the end, we will again add them together to make the overall reaction. So that is what is called the half reaction method. Okay, so what are the steps? These steps are important. In case if you don't know which one is the oxidizing agent, which one is the reducing agent, or which one is the oxidation half reaction, which one is the reduction half reaction, what you can do is assign the oxidation numbers to determine what is oxidized or what is reduced. That's not always a must step. That is always not necessary unless the question is specifically asking write oxidation reaction or reduction half reaction. Otherwise, you can just look at the species. As you do more practice, you will learn that. You can just look at the species and you can split into half reactions. Okay? So this is the first step. The second step is write the oxidation and reduction half reactions. Okay, let's assume we did that. Then what do you do? This step, this is the most important step, or most of the work is right in here. Balance each half reaction, but the following sequence is important. It is important that you balance it in this 4 steps following the sequence. How you start? First you start with balancing elements other than hydrogen and oxygen. Okay? Then you are going to balance oxygen. How do you balance oxygen? Whatever missing oxygens, you add water. Water is the oxygen provider. Then balance hydrogen by adding H+. Last step, balance charge by adding electrons. You have to memorize the sequence. If you go in some other sequence, you will not be able to balance the equations correctly. So, balance anything other than oxygen and hydrogen, then O first, H+, and then comes electrons. After you do that, multiply the half reactions by integers so that electrons gained and lost are the same. So you will see when each half reaction, probably you will have different number of electrons in each. So you will multiply them by appropriate numbers or probably the coefficients of each other to get them same. And in the end, add the 2 half reactions, cancelling things that appear on both sides. Make sure the equation is balanced according to the mass. Do just a final check by looking at the law of conservation of mass is followed or not. I know when you read there are a lot of steps. We will do examples, as I said, for the rest of the class. That's all we are going to do. Okay? This needs some practice, and some people just get it and some people need some practice. And I want all of you to get this. So, let's take an example which is given in the book itself. Let's just follow this. So, this is a reaction between permanganate ion and oxalate ion. The picture, it doesn't have to do anything with your reaction, it just shows you the picture. Oxalate is acidic and permanganate, when you add, oxalate is colorless, and permanganate with solution, when you add, the solution keeps losing its color, and at the end point it will retain that slight purple color. If you cross the end point, the solution again will have the dark purple color because of the permanganate ion. So this is the equation we have. MnO4 minus plus C2O4 2 minus gives Mn2 plus and CO2. We need to balance this redox reaction. Okay? So where do we start? First we are going to split this into 2 different reactions. Oh well, first we assign the oxidation numbers. Assume that you don't know which one is oxidizing, which one is reducing. So when you assign the oxidation numbers, you get manganese as +7, and after the reaction manganese as +2, and you get carbon as +3, and after the reaction carbon as +4. So manganese goes from 7 to 2, means it is gaining electrons, right? So that is reduced, therefore your reduction half reaction is MnO4 minus giving Mn2 plus. Similarly, what happens to carbon? Goes from +3 to +4, it lost an electron. So that is the oxidization reaction, C2O4 2 minus giving CO2. So there you have the oxidation half reaction, which is C2O4 2 minus giving CO2. First of all, carbon is not balanced, right? 2 carbons on the left side, only 1 carbon on the right side. Remember the sequence. The sequence is balance anything other than oxygen and hydrogen first. So just like in other chemical reactions, we will put the coefficient of 2 in front of CO2 to balance the carbons. Carbons are balanced. But what is not balanced now? Oh, well, oxygen is also balanced. Good. That was easy. So when we balance the carbon, automatically we balance the oxygen also. Right? Both oxygens, both carbons on both sides. Now we are going to do the charge balance. Of course, we don't have any hydrogens there, so we are not going to worry with the H+. Now what about the charge? Left side we see 2 negative charge. What is the charge we see on right side? 0. It's neutral, no charge, right? So if right side is 0, left side is 2 negative, we want to balance the charge. We cannot leave it as one side 0 and one side 2 negative. Remember, you cannot subtract anything from the equation. You can only add some things to the equation. So how can you make this equation both sides having same charge? The two options are either you take away 2 electrons from the left side, which I said not possible because you cannot take away anything from your reaction. So the only other option is add 2 electrons to the other side so that they both are of the same charge. It doesn't matter both sides are 0 or -2. As long as both sides have the same charge, we are good. So the only possible option is add 2 electrons to the right side. So we will put +2e. Now both sides have 2 negative charges, right? So we have just balanced this one half reaction, the oxidation half reaction. Now let's pick up the reduction half reaction, which is MnO4 minus giving Mn2 plus. Of course, Mn is balanced, but oxygens are not balanced. What do we use for balancing oxygen? Water. So we have to add 4 waters to the right side to balance the number of oxygens. So now we have both sides 4 oxygens, but while adding 4 waters to the other side, we also added 8 hydrogens along with that 4 water, right? 4 water contains 8 hydrogen. So to balance that 8 hydrogens on the right side, we are going to add 8H plus to left side. So now our equation is 8H plus MnO4 minus giving Mn2 plus 4H2O. Mass is balanced now, right? But charges are not. What is the total charge on the left side? 8H plus means positive 8, minus means -1. So what is the total charge here? Positive 7. What is the total charge here? The only species which has a charge is +2, Mn. So the total charge is +2. Is it the same on both sides? They are not. We need to make it the same. Again, we cannot take away anything. The way with the two options you can do is either you take a positive 5 from here, right? 7 minus 5 is 2. But can we take away anything?
Yeah. You take away the charge. You can't remove it.
Okay. So think of the charge also as something which you cannot take away. Oops. Okay. So your goal is, how can I make both side +2? How can you make both sides +2? 5 electrons to the left side, right? See, if you want to reduce this from +7 to +2, what you need is, you need 5 negative charges there. What will give you negative charge? Electrons. So you are going to add 5 electrons to the left side. So your equation will become like this: 5 electrons plus 8H plus MnO4 minus, giving Mn2 plus 4H2O. Now both of your half reactions are balanced. Next step is, it is important that we want to have the same number of electrons on both half reactions. Okay? So in the previous equation, do you remember how many electrons we had? Previous half reaction? 2. Here we have 5. So in order to get, when now we evaluate them together, so when you write them together, you can see that the first one has 2 electrons, the second one is 5 electrons. To make those numbers equal, we are going to multiply the reactions by each other's coefficients, coefficient of electrons. So we multiply the first one by 5, which is the coefficient of second reaction's electron, coefficient of electrons of the second reaction, and we will multiply the second reaction by 2, which is the coefficient of electrons from the first reaction, and we will get this one. Now we can see whatever is on both sides you can cancel. What do we see on both sides? Well, you are adding. Good. They are taking you through all the steps. Basically you can just keep everything left to the arrow sign, everything right to the arrow sign. Right there itself you can compare and you can cancel. Yes, that will come into the basics. Right now we are only working with the acidic ones. That will come next step. So here when we add everything on the left side is given left side of the arrow, everything on the right side, from both sides we give on the right side of the arrow. And what do we see? We see 10 electrons and 10 electrons on both sides, right? So we will cancel that. Is there anything else exactly on both sides? Or any species exactly on both sides? No. So whatever is left will give us the balanced equation. All right, let's do some practice. 20.2. Balancing redox equations in acidic solutions. So if you want to look at the sample exercise, Cr2O7 2 minus and Cl minus giving Cr3 plus and Cl2. So what I would do is, guys, I won't even care about the oxidation numbers right now. Unless the question is specifically asking, assign oxidation numbers and then do it. What I will do it, I'll pick up the Cr2O7 2 minus and look at the other side, Cr3 plus, right? So that will become my first half reaction, and then Cl minus becoming Cl2 is my other half reaction. So I'll just divide the two equations like that. Then we will pick up the first one, Cr2O7 2 minus giving Cr3 plus. Cr2 left side, Cr right side. So to balance that, first we add 2 in front of Cr3 plus. Then we see O7 on the left side, 7 oxygens. How do we add 7 oxygens to the right side? 7 water. So we add 7 H2O. Now when we added 7 H2O, 7 times 2, 14 hydrogens on right side. To balance that, we will put 14 H plus on the left side. So we have done the mass balance now. Now do the charge balance. What is the total charge on left side? 14 positive and 2 negative. 12 positive. Right side, what is the charge? Positive, well, positive 3, coefficient is 2, right? So, positive 6. So, we have 12 positive on this side, positive 6 on that side. It's easy to always bring it down to the smaller number on both sides, right? So, how can you bring positive 12 to positive 6? Add 6 electrons. So, that is why you have 6 electrons there. Now, so that reaction is completely done. Now, we will pick up the other one. Cl minus becoming Cl2. So, first of all, to balance the Cl number, we will put 2 in front of Cl minus. Then we look at the charge. Left side we have 2 negative charge, right side we have 0. So, to make it 2 negative on both sides, we will add 2 electrons on the other side. So, both equations you have balanced with charges and with mass. Now, we need to make that number of electrons the same. One side has 6, one side has 2, right? So, the second equation, the one which has 2, if you multiply that entire equation by 3, you will get 6 electrons there also. So, that's what is done there. So, you multiply that entire equation by 3, that makes it 6 Cl minus giving 3 Cl2 and 6 electrons. Now, add everything. Both equations left side becomes 1 now. Both equations right side become one big string now. Then compare carefully. What do you have on both sides? 6 electrons and 6 electrons were same on both sides. Eliminate them and whatever you are left with is the balanced redox equation. Once you have the redox equation also, again you can check for the charge balance. They should be alright. Let's check. 14 H plus means 14 plus charges. 2 minus means now positive 12. Then 6 minus 6 negative 6 plus, right? How about right side? 2 times 3 plus 6 plus. So the charges are balanced. Okay, let's do the first one on the practice exercise. Cu plus NO3 minus giving Cu2 plus and NO2. I will get a screen and write it down. So, Cu plus NO3 minus giving us Cu2 plus and NO2. This is our reaction, right? So, first we need the half reactions. Let me have the Cu reaction here. Cu giving Cu2 plus, and my other half reaction is NO3 minus giving NO2. This is the first step. You split into 2 half reactions. Now let's consider one by one. Well, Cu becoming Cu2 plus. Mass balance is good. 1 Cu, 1 Cu. There are no hydrogens and there are no oxygens. So we don't have to worry about adding water or H plus. So we are on to the charge balance state, right? How do we balance the charges? Cu is 0, Cu2 plus is 2 positive. So what can we do? Add 2 electrons here so that both sides are 0, right? Now both sides are 0. So we are done with that one. That one was very easy. Now let's pick up the other equation. NO3 minus giving NO2. Nitrogens are balanced. Oxygens are not. So what do? We need to add 1 water to the right side to make the oxygens balanced. Right? So oxygens are balanced now. Nitrogens are balanced. But when we add a water, we have hydrogens on right side now. There are 2 hydrogens. So what do you do to balance that? Add 2H plus to the left side. Let me write that as second step, guys, so that you can see the changes. So 2H plus plus NO3 minus, giving you NO2 and H2O. So mass is all balanced, charges are not. What is the total charge on left side? 2 positive and 1 negative. 1 positive, right? Right side is all 0. So how can we bring both sides 0? By adding 1 electron on the left side, right? So now both half reactions are balanced. Now we are going to see the number of electrons on what are the coefficients? 1 is 2 and 1 is 1. To make them equal, what can you do? Multiply this entire equation by 2. So that will be 2 electrons plus 4 hydrogens plus 2 NO3 minus, giving you 2 NO2 plus 2 water. So these are your two equations. This is the first equation. This is the second equation. The book is actually asking you to write one more step. I mean, we used to just look at them from, two different places and cancel. It's up to you. I'm not going to be,
But all you're canceling your electrons.
electrons. Well, later when you come to the OH thing, you will have water also to cancel. So at this state, you can basically just look at each of them and cancel the electrons. That's all you are going to cancel, right? So if you can look at both of the equations, in one equation 2 electrons are on the right side, the other equation 2 electrons on left side, so they get cancelled away. Now carefully write whatever is left on left side. From the first equation you have a Cu left on the left side, and from the second equation you have 4H plus and 2 NO3 minus. Now right side of the right side of the arrow you have Cu2 plus from the first equation, and then 2 NO2 and 2 H2O from the second equation. So this should be your balanced. Oh, did I make something? No. Good. So this is your balanced redox equation. Is that the answer? Okay. Shall we do the next one? So the second one read as Mn2 plus NaBiO3. Okay. So, well, let me look at the book itself and just write the half reactions. Mn2 plus and the other side is MnO4 minus. Okay. So one half reaction is Mn2 plus becoming MnO4 2 minus or 1 minus? Oh, 1 minus. MnO4 minus, and the other one is NaBiO3. NaBiO3 becoming Bi3 plus. Okay, so these are our half reactions. Let's pick up the first one. Well, manganese is balanced, oxygen is not. We have 4 oxygens on right side. Therefore, we are going to add 4 water to the left side, right? Because we want to make the oxygens okay. So the left side now has 4 water plus Mn2 plus, and the right side we have MnO4 minus. But when we added 4 water molecules, how many hydrogens we have on the left side now? 8. Therefore, we need to add 8H plus to the right side, right? Okay, now let's do the charge balance. What is the total charge on left side? Plus 2. What is the total charge on right side? Plus 8. And what happened to this one? plus 7. So plus 2 plus 7. Make both sides again. Always remember this, take the clue. When you have numbers like that, try to make both sides equal to the small number, right? So plus 2 and plus 7, you want to make both sides plus 2. So what you need to do? You need to add 5 electrons to the right side. So now your equation becomes 4H2O plus Mn2 plus giving MnO4 minus plus 8H plus and 5 electrons. So that is our first equation. Good. Second equation, NaBiO3 giving Bi3 plus. Only Bi is balanced. Before oxygen we need to balance sodium. What can we do? Just add a sodium to the other side. Okay? The sodium will exist as an ion on other side. So we will write this equation as, oops, started Na again. Yeah, I need Na. So NaBiO3 Bi3 plus and you will have an Na plus. That is the first situation. Now let's look at the O3. O3 means, what do you need to do? Okay, I'm going to write that right here. So NaBiO3 giving Bi3 plus plus Na plus and 3H2O, right? To make the oxygens okay. So 3H2O means we added 6 hydrogens to the right side. So that means now we need to add 6 hydrogens, 6H plus to the left side. So left side is 6H plus plus NaBiO3 giving you Bi3 plus and Na plus and 3H2O. Mass balance is good. Now look for charge balance. Total charge on left side 6 positive. Total charge on right side, what is it? What is the total charge on right side?
3.
Only 3. What happened to the positive charge on Na? Don't miss a thing, guys. Total charge on each side, that's what we are looking for. So here we have 6H plus means 6 positive charge. This is neutral, so nothing from there. Here Bi is giving 3 positive and Na is also giving a positive charge, right? So the total charge here is 4 plus. So we are comparing 6 plus and 4 plus. So to make it both sides 4 plus, the smaller number, what do we need to do? Add 2 electrons to the left side. So the left side becomes 2 electrons plus 6H plus plus NaBiO3 giving you Bi3 plus and Na plus and 3H2O. Each reactions are balanced. Now we need to figure out how can we make both sides electrons the same. 5 and 2, what is the best way? Multiply each of them by the other one's coefficient, electron coefficient. So multiply this first equation by 2 and multiply this one by the second equation by 5. So what do we get when we do that? So first equation by 2, let me write all that. So 4 times 2, 8 H2O plus 2 Mn2 plus, and this side we are multiplying by 5. So 10 electrons plus 5 times 6, 30 H plus 5 NaBiO3. Did I use everything on both left sides? Please keep checking, guys. Okay, now let's put the arrow. What all we have on the right side? So right side MnO4 should be multiplied by 2. So 2 MnO4 minus plus 16 H plus 10 electrons plus this equation is getting multiplied by 5. So 5 Bi3 plus, goodness, how much space I need, plus 5 Na plus 5 times 3, 15 water. Okay, such a long equation. Now I need to compare what exists on both sides. Of course, clearly I can see 10 electrons and 10 electrons. What else? We have some H pluses and water on both sides, right? We have 8 waters on left side and 15 waters on the right side. So 8 and 8 will go away, and what are we left with? So the left side 8, all of them will go away. Right side, after 8 is gone, we have 7 water left. How about some H pluses? We have 30 on the left side, 16 on the right side. So all of this 16 will go away, but from 30 when we reduce 16, we are left with 14. So whatever is now you have is your balanced redox equation. So you should have an equation which reads as 2Mn2 plus 14H plus 5 NaBiO3 giving you 2 MnO4 minus plus 5 Bi3 plus 5 Na plus. Is that the answer?
No, plus 7 waters.
Oh yeah, the 7 is right below here. Yes, plus 7 waters. Okay. I know a lot of work, but isn't that fun? I like this.
Until it gets more complex.
What?
Until it gets more complex.
Yes, but if you are thorough with this, with the next one we are adding only one more level.
Yeah, with the OHs.
Okay, so that is why I want you guys to be thorough with this, because all this and then just to take care of H plus we are going to add OH minus. But is this good? So far everyone is good? You know what? We will do the OH one in next class. I don't want to add that in the last 5 minutes, because when we do that we want to do some practice problem and really cement it. Right? Okay, let's stop right here. Thank you guys.